Nanoparticles are very interesting kind of structures, and we always talk about some special things, some special features of nanoparticles. In the last lectures, we have discussed the importance of nanoparticles and also the emergence of nanoparticles, from where it has started. Now, we are moving towards the core of the properties of nanoparticle, why it happens. Now, in this lecture and the coming lecture, we will discuss about surface energy, physical chemistry of solid surface. What is responsible for these nanoparticle properties? Yes, this is something that we shall study in this unit. We have discussed emergence of nanotechnology in two parts and bottom up and top down approaches. In this lecture, we are discussing physical chemistry of solid surface, surface energy. There are other issues, chemical potential as a function of surface curvature. We'll also discuss electrostatic stabilization, steric stabilization, elementary consequence of small particle size. Yes, surface of nanoparticles. We'll also discuss thermal phenomena, what happened when the temperature come into picture. Then diffusion law, surface in the nanomaterials, and consequence of surface energy. So basically this unit is based on surface energy, from where it comes, how it can be controlled, why should be controlled, and then what are the consequences of this surface energy. We will discuss these aspects in this unit. So we begin with physical chemistry of solid surface here. In this unit, first we will discuss about introduction of this surface energy. Then we will discuss why surfaces are so important in the case of nanoparticles. We will discuss this term surface to volume ratio, as most of the time we talk about this surface to volume ratio. What is surface to volume ratio and why it is important, we'll discuss here. And then in the end, we will discuss about surface energy, which is the most important part to understand nanoparticles. Take this activity before entering into subject. In this activity, on the left hand side, I have shown one big cube, a cube of dimension 4, 4 by 4 by 4. On the right hand side, there are certain small cubes. As a matter of fact, these cubes are obtained by the left hand side cube. Now these cubes are having dimension 2 by 2 by 2. Now my question is, can we create, can we obtain surface area of all cubes and volume of all cubes? In this case, start with the left cube. In this cube, the surface of each can be calculated. What will be the surface of each edge, each face? Yes, it will be 16 centimeters square. And how many surfaces are there? That is 6. So 6 into 16, this will be 96 centimeters square. Now the thing is, what about volume? The volume of this cube is 4 into 4 into 4, 64. So that is there. But if you take this right hand side, then we have divided this cube into 2. Now the surface area of a small cube will be 2 into 2 means 4. And since now these are the separate out, so for each cube, small cube, the surface area will be 4 into 6, that will be 24. Now you are, how many cubes you are having? Yes, 8 cubes. So 8 cubes, the total surface is 8 into 24. 192 centimeters square. So the surface area increased from 96 to 192. On the other hand, volume is still 64. Very interesting. Your area is increasing, but the volume is same. This can also be checked here by the sense that on the left hand side only one cube is there, so only outer surface can be used. But if you divide this cube into 4, 8 another cubes, so the inner surface will also come out. So surface increased, and on the other side volume is still same. So that is the importance of this. The surface can be increased. Now just thought about nanoparticles. If somehow by using any top-down approach you divide the bulk material into small, what will happen? The volume will be same, but the surface can change enormously. If the same surface change, then the surface to volume ratio will be very high. In the case of nanoparticles. Now take another example. This is little bit extended part. In this example, first I have shown a cube of 1 centimeter length. The length we have assumed is 3 inches here for each edge. In the second case, the area of each surface, they have taken 1.5 into 1.5 edge. In the third, 1, 1, 1. Now start with this. Suppose we have only one big cube, then the area of that each face will be 3 into 3, that is 9 inches square. But on the other side, if we increase the number of cubes, the area will also increase. In the first case, if the area of each face is 9 inches square and we have total 6 surfaces in the cube, then the area is 54 inches square. In the case of second, if you divide this big cube into two small cubes with a half edge, now the edge of each cube is 1.5, 1.5 length, 1.5 width. So by this you can cut total 8 cubes. Here the total A1 is there. In this case this is 8, and in this case this is 27. So if you increase the values by 1 to 8 and 27, you are bringing out surface from the inside. And so in the first case, the total surface area is 54 centimeter square. However, in the second, the total surface area is 108 inches square. Why? Because now you are using 1.5 edge. So for 1 it is 2.25. But since you are having 8 blocks now, so the total is this 2.25. If as we are having 8 blocks here, so you can do the things and you will get 108 inches square. It is double than the first. If you further reduce the size h of any cube, and now in place of 2 you create it into 3, so total 3 into 3 into 3 9, and 9 into 3 27. Now 27 blocks are there, so that value is 162. So we can conclude this here. The volume is continuous, the surface area is continuously increasing, but the important thing is volume is same. Volume is not increasing anywhere. So the surface is always increasing, but volume is not increasing. This will result in increase in surface to volume ratio. The increase in surface to volume ratio is very important for us. We will discuss in the next slides why it is so important. In this last slide, we have seen that if we reduce the size, surface increases dramatically. This increase in surface is very important. because if you move to reduction up to nano size, then surface is enormous as compared to volume is same. There is no change in the volume. When the surface is enormous, you can observe many properties. We know that nanoscale particles are not new in either nature of or science. However, the recent leaps in the areas such as microscopy has given scientists new tools to understand and take advantage of phenomena that occur naturally when matter is organized at nanoscale. This phenomena basically based on quantum effects and other simple physical effects such as expanded surface area. In addition, the fact that a majority of biological process occurs at the nanoscale gives scientists models and templates to imagine and construct new processes that can enhance the work in medicine, imaging, computing, printing, chemical catalyst, material synthesis. The important thing is we should not be confused or confined with this, that the nanotechnology is not simply working at smaller dimensions. As a matter of fact, we want to utilize the unique physical, chemical, mechanical, and optical properties that occurring naturally at this scale. When we reduce the size, the important thing is surface. Surface increases and it plays a lot of role. Nanostructures and nanomaterials possess a large fraction of surface atoms per unit volume. The ratio of surface atom to interior atom changes dramatically. If material in the bulk structure, then only exterior atoms can participate in any event, in any activity. But if you reduce the particle size, then now the interior atoms also comes out, and this changes this volume, surface to volume ratio dramatically. So that is very important in our case, and this gives a lot of information about the nanostructures. In the case of nanostructures, we move from classical physics understanding to quantum behavior, quantum size effect. We know that the atom size is of the order of 1 nanometer, and if we have a cube of iron of 1 centimeter H, the percentage of surface atom would be only 10 to the power minus 5%. It means out of 100, only 10 to the power minus 5 are outside and others are inside. Very small atoms are available on the surface for reaction. When I am using the word reaction, that means the reaction as a catalyst, the reaction in any medicines, only those atoms which are at the outside surface are available for reaction. That is the reason every process is slow. But suppose we divide the cube into small cubes and we divide in the range, suppose 10 nm in place of 1 centimeter. Now we are divided in the terms of 10 nm. In this case, the percentage of surface atom will increase by 10%. If it is increased by 10%, can you imagine how large number of atoms are there? From 10 to the power minus 5.0000001% to 10%. Definitely, if more atoms are available for reaction, the reaction speed will be very high, very high. Kinetics can be observed. In a cube of iron, of suppose we reduce from 10 to 1, then each atom will be on surface. Each atom will available to reaction. In this case, the reaction again very fast. That we want to explain here. If you reduce the size, this will increase the number of atoms available for reaction. And that is why reduction in size is very important for sensing applications or detection applications or fast reactions. And for those reactions which are possible only for higher temperature, now you can get even at lower temperature, even at lower concentration. The size reduction is very important here. However, we will also study that at this size reduction, the mathematics will also change. The statistics will also change. And obviously, we will move to quantum phenomena from classical. Here, it is shown that if the size of is 1 centimeter box, then the surface area will be 6 centimeters square. But if the size is 1 mm, then the surface area will be 60 centimeters square. But if the size is 1 nanometer, surface area will be how much zero you can count here. That gives the idea how the surface area is changing. Many zeros are there. That is very attractive in the case of nanoparticles. Increase in surface area is dramatic. This graph is plotted by taking another example. Here we are taking the example from palladium. We have a palladium cluster with some diameter, and then we are reducing the size of this cluster. As we reduce the size, this will increase the surface atoms. Now you can see from the first case, from the right hand side, see here the size is 63 micrometer, and in this case you can see that very small atoms are at surface. Now, as you decrease the size of the palladium crystal, this will move in upward direction towards left. The graph is moving. Why we are having this dramatical change in the ratio of surface atom to interior atom? Because now more atom will participate. As we reduce the size to 7 nanometer, this will increase the participation to 35%. If we reduce to 5 nanometer, this will move to 45%, and so on. To 1.2, if you move to 1 nanometer about, that is 76%. So from almost 0.9% to 76% rise in surface atoms. Reduction in size improves the surface atoms. We have also mentioned here the variation of surface energy with particle size. As the surface area increases, the edge can also be increased. You can see here. The edge will increase, and this will also increase surface energy or edge energy. We can calculate this. In the case of nanoparticles, drastic changes observed. You can see here, if you are moving from 0.77 to 0.1, change is there, but not drastically. But if you move from 0.77 to 10 to the power minus 4, it changes from someone to 10 to the power 4, 10 to the power 8 energy change. That is very interesting. We have to take care of all the examples. We have taken few examples from palladium for iron, and tried to understand this and how surface increment is useful for us. As we have shown, the total energies are negligible when cubes are large, but the energy becomes significant for small particles, for very small particles. When the particle change from centimeter to nanometer size, the surface area and the surface energy increase 7 order of magnitude. That is interesting for us. Since we have vast surface area in nanostructures, the nanostructure material possesses huge surface energy and thus are thermodynamically unstable or metastable. The surface energy, free energy, or interfacial free energy quantifies the disruption of intermolecular bonds that occurs when surface is created. In the physics of solid, surfaces must be intrinsically less energetically favorable than bulk of materials. As a matter of fact, the molecules on the surface have more energy compared with molecules in the bulk. And this is the driving force the molecules have. The surface energy may therefore be defined as the excess energy at the surface of material compared to bulk. Actually, it is the work required to build an area of particular surface. If we cut the bulk particle into small particle as we shown in the last slides, then cutting a solid body into pieces disrupts its bonds and therefore increases free energy. If the cutting is done reversibly, then the conservation of energy means that the energy consumed by the cutting process will be equal to energy inherent in two new surfaces created. The unit surface energy of material would therefore be half of its energy of cohesion. Surfaces often change their form away from the simple cleaved bond. They are found to be highly dynamic regions which readily rearrange to or react so that the energy is often reduced by such process, passivation or absorption. In the case of nanostructures, we always talk about fabrication, processing of the materials. And one of the biggest challenge we face, how to overcome surface energy. Because the surface energy is very high. And this surface energy prevents nanostructure to grow in size. And this is driven by reduction of overall surface energy. So that is important. It is a great challenge. So always we talk about how to overcome this, to create nanoparticles, to grow nanoparticles. So whenever we are working with the nanoparticles, we must think of this issue of surface energy in detail. In order to produce and stabilize nanostructures and nanomaterials, it is essential to have good understanding of surface energy and surface physical chemistry of solid surface. We must take care of these things. First thing is we have to know the size of the nanoparticles. Now, if you want to create those nanoparticles, then how you can stabilize those nanoparticles. Production is important. Keeping it stabilized is important. For this, it's essential to have good understanding about this of surface energy and surface physical chemistry of solid surface. In this series of lectures, we will study the surface energy. We will review the surface energy first. Then we will discuss possible mechanism, how it can be reduced to create nanostructures. I would like to add one important thing here. We are always interested in various size, various shapes of nanostructures. And everything, say, size, shape, depends on energy. So the understanding of this energy, understanding of energy of the surface, energies in the bonds is very important. These things are important to stabilize the particles. We will discuss these properties and contents in these lectures. We will start with the surface energy, then we will move to how to overcome in the next lectures. So, in this lecture, we have studied the idea of reduction of bulk materials. We have studied what happens if you reduce the size. If we reduce the size, the area increases, the surface area increases. And the basic meaning of increment in surface area is the particles, more particles on the surface, on the outside from the interiors come. And when more particles are there, this may occur due to disruption of bonds. So more energy is there, more surface area is there, and more surface area means more energy is there. That energy put a great challenge for us to grow. The materials become unstable at this stage. That is the reason we have to take care of understanding of surface energy. We will discuss this issue in detail in this chapter. After learning about the surface energy, we will also discuss other aspects about potentials and energies. So we stop here. In the next lecture, we will study about more detail about surface energy and then how to overcome this. The chemistry of the surface we will discuss.